Hey, hi everyone. So for this video, we'll discuss differential equations, and there's really a lot there are a lot of topics in differential equations, but I will get through the most of it. So I hope you can bear with me. So let's begin with the outline. So actually, there are a lot of things that is supposed to be in this slide, but I simplified it into three general sections. So you have the solution for first order differential equations. Actually, it should be linear homogeneous and linear non-homogeneous differential equations and applications of differential equations. So the first one is actually just classification. So it is important. It is quite important to distinguish different types of differential equations, and let's figure out which one are linear and nonlinear. So the first one, we have this differential equation. So the categories of nonlinearity or the linearity. So the first one is uh, the dependent variable should have an exponent of 1, right? And then 2, no, including its, no, including all of its derivatives. And then the second one is a dependent variable has no transcendental functions. No transcendental functions. Where is it? No transcendental functions. And then there should be no multiplication, no product of the dependent variable. So as you can see, we're only checking the dependent variable. So if any of these three is violated, no, then it is already nonlinear. So if all of this is a characteristic of our differential equation, then therefore it is linear. So it is easier for a differential equation to be nonlinear than it is to be linear. And usually we don't have a solution for most of the nonlinear functions, but we do have uh, we do have methods, no, for linear differential equations. Okay, so the first one, let's identify first which is the dependent variable. So the dependent variable here is the numerator derivative. So the dependent variable here is dy. So if dy has an exponent of 1, okay, it has an exponent 1, including its derivatives, right? So this is just third derivative, second derivative, first derivative. It's not squared of dy over dx, no? So that is a different thing. So check for number 1. For number 2, there are no transcendental functions of the dependent variable. So y and the derivatives of y. So there is no transcendental function. What are transcendental functions? If let's say we have sine y or ln y or e raised to y, then it will be a violation. So we're good with 2. So number 3, we have no product of y with itself or with a derivative of or a dependent variable. The derivative of the dependent variable. So one is linear. Okay. For number 2, the violation here is no transcendental function of the dependent variable. So the dependent variable is y because we have this, no? So therefore, this is nonlinear already. It violated 2. Okay. For number 3, okay, so the violation here is 1 and 3. So we have a square here, and then we have a multiplication of these two dependent variables. So dependent variable y and the derivative of the dependent variable. So this will be nonlinear. And then for the last one, so what is it? So you have to check if what is the dependent variable. So the dependent variable here is actually x. So it depends on how it is shown to figure out what is the dependent variable. So the dependent variable is x. So since we have a multiplication of x with this, nonlinear and also transcendental function of x. So this will be nonlinear. Okay, it's that easy, no? So let's now try solving differential equations. So if we have this differential equation, we don't know where to start. No? You first try to figure out what are the steps, no? So the first thing you have to do is try to identify what type of differential equation is this. No? So basically, you should have to start with the simplest one, check if it is variable separable. So if it is variable separable, if it is a homogeneous, no? Homogeneous differential equation, if it is exact, if it is non-exact, if it is a linear differential equation or first order linear, actually it could be first order linear differential equation or Bernoulli differential equation. So these are the general differential equations for first order. So this is the first order differential equations, meaning it has the equation has the first derivative as its highest derivative. No? And then for higher order, so we have the higher order, we only have higher orders. So this will be, well, the general linear differential equations that is either homogeneous. Actually, this is only one, no? This is either homogeneous. So there is a different definition of homogeneous here and the non-homogeneous. So I can discuss everything here. I'll just try discussing some of it. So let's get into it for later. Okay, so this first one is what type of differential equation we have a variable separable. No? Actually, it is also homogeneous. No? Uh, is it homogeneous? Actually, no. Actually, no. Sorry. So this is a variable separable differential equation. So what does it mean? So if you rewrite this as dx over dy is equal to 2yx, then you can separate everything else that is y, the left, and everything that is x to the right, so that the differential equation will look like this. Sorry, we can transfer the y here using cross multiplication. So this will be y, and then equals to 2x dx. Ayan. Okay, so if this is variable separable, then we can integrate this differential equation separately, or we can use an integrator operator to eliminate this dy or and then dx variable. So this will become ln y is equal to x squared and then plus c. Okay, so this is already your answer, but it is not over. You can further simplify this by what? No? By using the e, no, or exponential function. So if you do the e raised to, or if you use the exponential function, this will be just e raised to ln y is equal to e raised to x squared plus c. So why did we use this? So we can represent y explicitly, meaning if this is explicitly, then you can write this as y is equal to blank. No, this is basically what this an implicit function is. You can write the dependent variable as a single variable that is raised to 1. No? So if you do this, we can simplify this as just y. So it will cancel out since the logarithmic function, the natural logarithmic function ln, is the inverse function of the exponential function. And then this one, this can also be simplified as e raised to x squared times e raised to c, right? And property of differential equations is that, well, in integration, the property of constants is that if this is still a constant, we can rewrite this as still a constant. So we can write this as y is equal to c e raised to x squared. So this should be another answer. No? So these are both equally right, but it is much more easier to read this than this one. It is harder to imagine logarithmic functions. It is easier to imagine exponential functions. Okay, so for this one, how about this one? So this is not variable separable, right? We cannot separate the variables x and y. This is not homogeneous. So homogeneous differential equation has the same degree, meaning not the degree. It has a definition in differential equations, but the same exponent value. So we have here 3, we have here 1, no? So raised to 1, and then we have 3, and then 1. So basically, this is 3 because we have 2 plus 1. No? So 2 exponent, 1 exponent. So this is not homogeneous. So we should try different method. We can try for exactness, no? Or we can try if this is an exact differential equation. We have the test for exactness. exactness. So the test for exactness is my next, no? So the partial differential of m with respect to y is equal to the partial differential of n with respect to x. So which is m, which is n, which is n, which is y, which is which. So the general form of first order differential equation is we have m of x, sorry, not this one, m of x dx plus n of y dy. So equals to 0. So just remember that from the alphabet, m is first and then n, and it also x is first before y. So the partner here is m and x and n and y. So to find the partial derivative of m with respect to y, we have to find the derivative of m, no, with respect to y. So the partial derivative. So the partial derivative of m with respect to y, as you can see here, so everything will be represented as a constant, but the y variable will be differentiated. So the derivative of y is 1. So this will be just a constant, so a coefficient, no? 3x squared will be a coefficient since again we are finding the partial derivative. And then this will be 0. Sorry, we have to write this pala, no? Sorry, I will write this down first. And then equals to partial derivative with respect to x of x cubed plus 2y. So to simplify this, again, we have here 3x squared. Okay, so this will be 0 since we don't have a variable y. And then partial derivative with respect to x. So partial derivative of x cubed, we have 3x squared. And then the partial derivative with respect to x of 2y is 0. So as you can see, this is therefore exact. So how do we solve exact differential equation? For exact differential equation, there's the method called the direct integration. So basically, just integrate this. So if you integrate this, direct integration, you can just integrate this. You have with respect to x, right? So this should be with respect to x. So this will be the integral of 3x squared is x cubed. So you will assume that y is now a constant. So like partial derivatives, we have in somewhat way partial integral. No? And then we have here negative 3x squared. So if you integrate this negative x, we have, negative 6x, we have 3x squared. And then for the other one, you have to integrate this with respect to dy. Sorry, with sy. So this will have a y here. So we have x cubed and then y and then plus y squared. So what should we do here? So basically we have to just combine this two. If there is a repetition, then we combine this as one. Although we do not add this two, no? So the answer here should be x cubed y minus 3x squared plus y squared is equal to c. So this should be your final answer. It's that simple. Okay. Okay, so we have another problem here. So y prime is plus y over x is equal to 1 x cubed y cubed. Okay, this is a little bit challenging, but we have a formula for this. So the general formula for first order linear differential equation or first order Bernoulli differential equation is just this. No, you will just utilize this all the time. So you have dy over dx plus p of x y is equal to y raised to n. Okay. Sorry, q of x pala to, no? Forgot. Why can I erase this? Q of x. Okay. And then y raised to n. So to be able to solve this, we have to use the integrating factor phi. So this is the first step, second step, and then this is equal to 1 minus n. Sorry. E raised to 1 minus n pala to. E raised to 1 minus n. The integral of, sorry, I don't usually memorize this. No, this is just spontaneous, so I cannot really remember everything right now. So 1 minus n and then equals to, you have 1 minus n integral of p and then q of x dx. Okay, that's a lot of formula, no? But basically, if you have a function that looks like this, okay? So sometimes the yn can be 0, no? So basically, if n is equal to 0, this will be first order linear differential equation. If n is equal to 1, this will actually become a variable separable differential equation. But if n is not equal to 0 or 1, but an integer n, usually integers lang, no? But I don't have a proof. It could be, I won't discuss that anymore, but if this is not equal to 0 or 1, this will be Bernoulli. Okay, so as you can see here, based on this equation, differential equation, we can say that the p of x here is equal to 1 over x, right? The q of x here is equal to 1 over x cubed, okay? And then the n here is negative 3, okay? So based on this form, so this will become, if we raise this upwards, this will become y raised to negative 3. Now, we can just use directly the formula. So the second step here is to find the integration or the integrating factor. So the phi here is equal to e raised to 1 minus n. So you have 1 minus 1 minus negative 3 and an integral of p of x dx. So you have 1 over x dx. So the phi here will be equal to e raised to 4 and then ln x. So an interesting property of logarithmic functions is that we can transfer this 4 here. So phi is equal to e raised to ln x raised to 4. Now we can cancel this out, so therefore the integrating factor is x raised to 4. Okay, so we have the integrating factor. We can substitute this value here. So we're good with q of x. We have n. We have everything. Okay, so therefore we just use this formula to make things faster. So phi is equal to x raised to 4 using this formula, and then y raised to 1 minus n. We have, this will be just 4. Okay, is that okay? So 1 minus negative 3 is 4, and then equals to 1 minus n, which is, again, 4. Integral of phi, we have x raised to 4. P of x is 1 over x cubed, and then dx. So if we simplify this integral, this will just be x dx. So we have 4x squared. Oh, is that right? Not right. This doesn't seem right. Okay. I'm just paranoid that this is too easy, no? So x squared over 2, right? And then you have x4, y4. So this will cancel out into 2. And then this is an answer already, no? Anyways, you can just box this out. But what if you need to simplify this? So to simplify this, just sorry, we have a plus c. We forgot the plus c pala, no? So we're integrating, so there should be a plus c here. So plus c. Okay, so if you want to simplify this as an explicit function, usually Bernoulli and first order linear differential equation are expressible as an explicit function of y. So you have here y raised to 4 is equal to, so divide both sides by x raised to the fourth power, so we have 2 over x squared, and then you have plus c over x raised to the fourth power. So to simplify this, you have y as the fourth root of 2 over x squared plus c over x raised to 4. So this will be your simplified answer in an explicit function of y. Okay, it's pretty fast. Now, how do we solve this? So if your differential equation is first order, we have the following, I've discussed this. So you have the following options. First order meaning first derivative. But if your function is of higher order, so we have second, third, and so on. But this should be linear, no? Take note that the one solvable is the linear differential equations. So you have to take note of that. And I won't have non-homogeneous, although you have to do this as your homework. You have to solve non-homogeneous differential equation. But for homogeneous, this is pretty easy to solve. Okay, so if you have something like this, so you have y double prime plus 4y. The way to solve this, since this is a second order differential equation, Then, assuming that this is linear, no? But we know that this is linear, no? So this is we know that this is linear, okay? And it only has constant coefficients. So another constraint that we should take note of, coefficients. We just use the auxiliary equation. So basically, we can transform this into its auxiliary equation. That's what we call it. Wherein we just change the variables, no? Or if let's say we have y double prime, this will become m squared. If we have y triple prime, you have m cubed, and so on. So y to the fourth power, sorry, not fourth derivative of y is m to the fourth. So if you have y, this is equal to actually 1. Okay? And then if you have, I think that's it, no? So it should be transformation, no? So this should be transformation. So this will now become m squared. So this will be m squared plus 4 is equal to 0. So basically, we want to solve this auxiliary equation, and then later on I will discuss how should you treat the answers, no? So if you simplify this, how do you now solve this? You do not have a real solution to this, right? So no real solution to this. So we have anyways, we have to transpose this to the other side. So we have m squared is equal to -4, and then finding the square root, you have m is equal to the negative square root of 4. Okay, so the square root of 4, I mean, we can separate this as -1 times 4. Well, we can simplify this the square root of 4. So m is equal to 2 times the square root of -1. Or we know that we know that -1 is I, so we have 2i. So this will be your answer, no? So this is actually a complex conjugate, so actually this should be positive or negative. But anyways, if you have a complex value, then the formula for that, this is the solution of well, this is actually case 3. Please read my notes, no? Wherein the solution, the general solution is y is equal to e raised to ax, and then c1 cos bx plus c2 sin bx. So what is this? So the a here and the b here are basically just the complex number, no? So you have a plus bi as your complex number. So this is your real part, sorry, I cannot erase it. Yeah, oh, I erase everything. Real part, and then this will be your imaginary part. So we just substitute the values, no? So since this is just 2i, then therefore this is the imaginary part. So therefore this is just b. So 2 is equal to b. Now to solve this, you have an answer which is y is equal to e raised to what? No? So since we don't have a, so a is equal to 0. So we have e raised to 0x. And then you have c1 cosine 2x plus c2 sine 2x. So we can cancel this out. So y is equal to, so this will become 1. So we have c1 cos 2x plus c2 sine 2x. Okay. So I think just read my notes regarding the cases. So for case 1, you have real and distinct. Real and distinct. So basically, you just use y is equal to c1 e raised to mx plus c2 e raised to m2x. So we have the first m and so on. And then for case 2, you have real and repeated. So similar to partial fractions, we have these 4 cases. So the general solution is if it is repeated, you have c1 e raised to mx plus c2x e raised to mx plus c3x squared e raised to mx and so on. And then for case 4, it is a combination of complex and repeated. Okay, so actually this is just complex and distinct. Okay, So just review this, no? And this is quite important. Okay. I think this is the last one. So for the last one, we have this problem. So the population of a certain country is known to increase at a rate proportional to the number of people present living in the country. If after 2 years the population has doubled, and after 3 years the population is 20,000, find the number of people initially living in the country. So this is an exponential growth problem. No, you can already say so. There are three general applications that is discussed in differential equation for applications. So the first one is exponential growth and decay. We have the Newton's law of cooling, and then we have mixture problems. Although this can grow into also electrical circuits and also mechanical systems. So usually this is not included, but most of the time it's just this three. So let's derive this from the base, no? So the population of a country is known to increase at a rate proportional to the number of people. So basically, we have dy over dx is dy over dt. We have a function of time is proportional to y. So if you simplify this, if regarding proportionality, you can say also that dy over dt is equal to ky. Okay. If after 2 years the population has doubled, okay, so before we do that, we can solve this differential equation, right? This is variable separable. So if this is variable separable, the solution for this is we have dy over y is equal to k dt. So we integrate this both sides. So we have ln y is equal to kt, and then plus c. If we simplify this will become y is equal to c e raised to kt. So this will be your solution to the differential equation. That is the assumption here. So assuming that y is the number of people, no? So therefore your function here is y of t is equal to c e raised to kt. Now the given here is after 2 years. So after 2 years, y of 2, the population has doubled. So sorry, I think I have to simplify this first, no? So yeah, let's simplify this first. So given this first, if y is equal to if t is equal to 0, we have what, no? So if you substitute this as 0, so you have c e raised to 0, right? So y of 0 is equal to c. Okay? So you have the constant is equal to y of 0, or just the initial condition, y sub 0. So y of t is actually not, to give significance to c, what does that mean? That is just the initial population, or the initial number of amount, or the initial number of present. So you have y o e raised to kt. Now, if let's say y sub o is the initial value, so it has doubled after 2 years. So y of 2 is equal to 2y sub 0. And after 3 years, so y of 3, you have okay, it's okay. It's okay, it's okay. And then 20,000 for y of 3. So 20,000 here. And then after that, what's next? So that's the given. So we can just substitute this to our equation. Maybe we can find something, no? So basically, if we utilize this, no, to combine to this, what happens is we have 2y sub 0 is equal to y sub 0, and then e raised to k times. So we know that the time is 2 here, so we have 2k. Okay, so basically we can cancel this out. So we have 2 is equal to e raised to k. Okay, so you can find the value of k here if you want, or I will just find the exact, no, the exact value of k, which is um how do we do this? I'm having a mental block. So we can just use ln, no? So ln2 and then equals to ln e raised to k, not x but 2k. So this will become ln e and then this will be 2k. So this ln2 is equal to 2k. So k is equal to ln2 over 2. Okay, so we have a value of k. And then after that, we can solve for what's next? So y of 3 is equal to 20,000. So we can find the initial population using this. So using this again, we can have a new y sub 0. Wait. Sorry about that. So you have here y of 3. So y of 3 here is you have 20,000 and then y of 3 basically time is equal to 3. So y sub 0 e raised to kt. We already know what is k. So this is ln2 over 2 and then t is equal to 3. So to solve for y sub 0 is or can be solved using this. So y sub 0 is equal to 20,000 over we have e raised to 3 halves ln 2. So solving this using your calculator, we have 20,000 over e raised to 3 halves and then ln 2. So the answer should be 7071. 7071 or something close to this. Okay, so that's all. I hope you learned something here, or you remember something in your differential equations. So thank you guys for listening and see you guys tomorrow or next meeting. So bye bye.